The physiological collapse really begins with environmental hygiene. Low oxygen and high ammonia chemically blind the innate immune system.
which allows these massive cysts to invade, anchor themselves, and structurally destroy critical organs.
But understanding how to optimize pharmacological agents like praziquantel to penetrate the host's fibrotic defenses provides a safe, highly effective cure that protects the producer's bottom line.
A whole new era of communication in the global aquaculture industry is coming. Now you have the brightest minds in aquaculture right in your pocket. And what's best? You can listen to all of them while driving to a farm, traveling, or running errands. It's never been this good, and it's never been this simple. Welcome to the Aquaculture Podcast Show, the first AI-based podcast in aquaculture, where you'll find cutting-edge insights in everything that's working in aquaculture, nutrition, health, and production. Inspired by the 2024 article titled, Evaluation of Praziquantel Effectiveness in Treating Nile Tilapia Clinostomid Infections and Its Relationships to Fish Health and Water Quality, by Mahdy, Olfat A, et al.
Imagine a commercial aquaculture facility where the water is, demonstrably more toxic than a wild city drainage canal.
Yeah, it sounds completely backward, but it's exactly what we're looking at today.
Right. And inside this managed facility, the fish are harboring these yellowish, centimeter-wide parasitic cysts that are actually physically replacing the architectural tissue of their kidneys.
Just a fascinating look at how severe environmental stressors can completely crash a fish's innate immunity.
Exactly.
Feed formulation software is stuck in the past. Most tools haven't evolved beyond basic least-cost optimization. A Diet Forge changes that. It's an AI-powered platform with nonlinear ingredient modeling for enzymes and additives, cost per gain and maximum profit optimization, and real-time collaboration like Google Docs for nutrition. Every recommendation is grounded in world-class research, built for modern nutritionists who need more than legacy desktop software can deliver. Work seamlessly with your team and optimize the way modern operations demand. Try dietforge.ai free today. Feed formulation, finally modernized.
Welcome to your deep dive. Today, we are unpacking this biological collapse for you. Our mission is to explore how that open door leads to massive clinostomid infections and, crucially, how we can optimize a classic pharmacological treatment to clear those infections safely.
And we're pulling all of this from a really robust 2024 study. It's titled Evaluation of Praziquantel Effectiveness in Treating Nile Tilapia Clinostomid Infections and Its Relationships to Fish Health and Water Quality, published by Mahdy and colleagues.
So, starting with water parameters, the documented. Because the baseline data here really challenges how we view these high-yield production systems.
Right. Mahdy and colleagues ran parallel analyses on 300 fish, 150 wild-caught from open water drains, and 150 sourced from private farms in Egypt.
And when they sampled the farm water, the dissolved oxygen was sitting at just 4.1 milligrams per liter, which is, really low.
Yeah, and the ammonia levels were incredibly high, logging in at 1.58 milligrams per liter. Plus, they found severe coliform counts from local microorganisms.
Which is wild. I mean, we know large-scale commercial aquaculture it's an incredibly sophisticated industry doing vital work to feed the world. So how does a highly controlled, financially incentivized facility end up with worse water metrics than a wild drainage canal?
Well, it is usually a direct consequence of unmitigated overintensification. To maximize those crucial harvest yields, facilities will sometimes push stocking densities just a bit too far beyond the carrying capacity of the water.
Right. You get a massive biomass of fish that require heavy nutritional inputs.
Exactly. And the biological reality is that, a percentage of that feed goes unassimilated. That results in heavy organic waste loading at the bottom of the tanks.
And then the aerobic bacteria that are breaking down all that organic matter just rapidly consume the dissolved oxygen.
Yes, pulling it down to that dangerous 4.1 threshold.
Yeah.
And the nitrogenous waste from both the uneaten feed and the excretion drives that ammonia spike.
And specifically, the unionized fraction of that ammonia is highly toxic, right? It permeates the gills and enters systemic circulation.
Which triggers a massive sustained stress response. The fish's neuroendocrine system goes into absolute overdrive, chronically elevating blood levels of cortisol.
And those stress hormones are what actively suppress the immune system, like they physically inhibit the white blood cells.
Exactly. Their cellular defenses are essentially chemically blunted by their own stress response.
So their immune system is practically offline, just trying to survive the water. And the vectors delivering these parasites are just, well, sitting right there on the edge of the tanks.
Right. The researchers documented heavy populations of snails in the water and piscivorous birds like egrets and herons hanging around the farms.
Because those birds shed the parasite eggs into the water via their feces.
Yeah, the eggs hatch, infect the snails, multiply, and then emerge as free-swimming larvae seeking out a secondary host, which is the fish.
And with the farm tilapia being so immunologically suppressed, those larvae encounter basically zero resistance penetrating the skin and gills.
None at all. And once they were inside, Mahdy and colleagues used genetic profiling of specific mitochondrial genes to pinpoint exactly what they were dealing with.
Because that specific genetic target lets them clearly distinguish between closely related species, right?
Exactly. They definitively identified 3 distinct species: Clinostomum complenatum, Clinostomum fulcrocrassus, and Euclinostomum heterostomum.
And the morphology of these things is just staggering. We're talking about highly visible macroscopic cysts. The Clinostomum species look like these yellowish, grape-like structures.
While the Euclinostomum cysts were grayish-white and shaped a bit like peas.
And some of them reached 9 millimeters in diameter, which, for a parasite embedded deep in host tissue is just massive.
It is a massive biological footprint. They were heavily encysted in the mouth, the gills, the muscle tissue, and the kidneys.
And when the researchers used high-resolution imaging to map them out, you can really see how they secure themselves.
Oh yeah, they have incredibly thick outer layers and these massive suckers, an oral sucker and a huge ventral sucker surrounded by a sponge-like fold.
So they aren't just resting in the tissue, they are violently anchoring themselves in there.
Right, causing severe pressure and mechanical displacement of the fish's internal architecture.
And that mechanical displacement triggers this massive systemic shock wave. You can see it immediately in the hematological data they pulled.
The erythrograms showed a huge drop in red blood cell counts and hemoglobin. The fish were suffering from profound anemia.
Because the parasites are actively siphoning nutrients and causing localized hemorrhaging, right?
Exactly. And alongside the anemia, the blood panels revealed a massive spike in total white blood cells, specifically driven by eosinophils.
Which is the classic signature of a large multicellular parasite infection.
Yes. The host's immune system is desperately trying to mount a defense. But given the scale and thick capsules of those cysts, those immune cells are largely ineffective.
And the biochemical markers were just as alarming. Severe drops in blood proteins and a huge spike in blood glucose.
That hyperglycemia is basically the fish dumping glucose into its bloodstream to fuel a fight-or-flight response that it fundamentally cannot win.
But the real tissue destruction showed up in the organ-specific markers. They recorded massive serum elevations of liver enzymes.
Right, those intracellular enzymes are supposed to stay sequestered safely inside the organ cells. When they spike in the blood, it means the cellular membranes of those organs are actively rupturing.
And they saw the exact same thing with the kidney markers. Creatinine and uric acid levels were highly elevated.
Which indicates the kidneys were failing to filter waste products from the blood.
But, a critical question comes up here. If the fish are already swimming in highly toxic water, how do Mahdy and colleagues know these organ changes are from the parasites and not just ambient ammonia toxicity?
That is where the microscopic tissue analysis comes in. It answers that unequivocally. They didn't just see diffuse cellular swelling from bad water.
Right. They actually observed the parasites physically embedded deep within the functional kidney tissue.
Exactly. The tissue slices showed the host body actively trying to isolate the threat by building these dense, fibrous connective tissue capsules entirely around the cysts.
And right next to those capsules, there was severe localized tissue death. The kidney was literally being replaced by the physical mass of the parasite.
It is a complete structural takeover.
So, with the fish's bodies basically failing, the researchers pivoted to testing a pharmacological solution to save them.
Yeah, they designed in vivo trials utilizing praziquantel, which has been the frontline therapy for these types of flatworm infections since the 1970s.
It is an absolute classic, but its efficacy in aquaculture really depends entirely on the delivery protocol.
Exactly. They tested various bath concentrations and exposure durations to find the optimal therapeutic window.
And they started with a short duration, high concentration bath, right? Exposing the fish to 8 milligrams per liter for 4 hours.
Right, but that aggressive approach only achieved a 44% mortality rate for the parasitic cysts.
Here is where it gets really interesting, though. The winning protocol was a much lower dose, just 2 milligrams per liter.
But with a prolonged exposure time of 24 hours, and they repeated it twice.
And that achieved an 83% cyst mortality rate with 0% mortality for the fish, which is amazing.
It really highlights the complex interaction between the drug and the physical barriers constructed by the host.
Right, because why does a slower, lower dose work so much better than just blasting them? We have to look at how praziquantel actually kills the worm.
Well, it operates by binding to voltage-gated calcium channels on the parasite's outer layer. It triggers this massive, uncontrolled influx of calcium ions.
Which causes instantaneous paralysis of the worm's musculature.
Exactly. And then the drug induces rapid vacuolization, basically forming massive bubbles within that outer layer, causing the parasite to physically disintegrate.
But the drug actually has to reach that outer layer first. It has to act like a slow biological marinade, right? Dissolving in the water, crossing the gills, entering the bloodstream.
And once it reaches the tissue, it hits that formidable barrier we mentioned earlier, those dense, fibrous connective tissue capsules the fish built around the cysts.
Because fibrotic tissue has very, very poor blood flow.
Exactly. A short, high-concentration blast might spike the drug levels in the blood, but it simply doesn't have enough time to permeate that thick fibrotic wall before the drug begins to clear from the fish's system.
So the prolonged 24-hour protocol maintains a steady, lethal concentration gradient. It gives the drug the necessary time to slowly seep through the host's fibrous capsule.
Right, to navigate the cyst fluid and finally bind to the parasite's calcium channels.
That makes total sense. And another critical point Mahdy and colleagues highlight is the food safety aspect, which is obviously huge for big ag commercial producers.
Oh, absolutely. Praziquantel is rapidly metabolized in the liver and excreted via the kidneys. Decades of data confirm it does not heavily bioaccumulate in the muscle tissue.
Assuming the kidneys haven't been completely replaced by cysts, of course.
Right, renal clearance relies on functional tissue. But the rapid elimination half-life means the fillets are safe for consumption shortly after treatment. It provides a targeted solution without leaving hazardous residues.
So tying this all together for you, the physiological collapse really begins with environmental hygiene. Low oxygen and high ammonia chemically blind the innate immune system.
Which allows these massive cysts to invade, anchor themselves, and structurally destroy critical organs.
But understanding how to optimize pharmacological agents like praziquantel to penetrate the host's fibrotic defenses provides a safe, highly effective cure that protects the producer's bottom line.
The data from Mahdy and colleagues really illustrates that in high-performance production environments, veterinary medicine goes hand in hand with rigorous environmental management.
Absolutely. And there is one more striking implication here regarding the vectors.
Right, the piscivorous birds, the egrets and herons spreading the eggs.
Because, those avian vectors are not static. Migratory flyways are currently undergoing rapid historic shifts driven by changing global climates.
Habitats are expanding. Bird populations are altering their traditional routes in response to shifting temperatures and water availability.
Which means, if climate change continues to alter where these birds travel, they could carry these parasites far beyond their historical ranges.
Exactly. We could see these specific macroscopic invaders introduced into massive commercial aquaculture hubs that have entirely zero evolutionary history or adapted immunity to them.
Which is a sobering thought. The environmental stressors we analyze today might soon be facilitating novel outbreaks on a global scale, and the industry will need to be ready.
They absolutely will.
Well, thank you for joining your deep dive today. Keep questioning the systems around you, and we will see you next time.
If you enjoyed this episode, make sure to follow the Aquaculture Podcast Show on your favorite platform. And don't forget to follow us on LinkedIn, Instagram, and Facebook to stay updated on the latest episodes and industry insights. Thanks for tuning in, and we'll catch you next time.